The electronic and nuclear wave functions are normally separated by the very large scale differences. We analyze a system where we surprisingly find evidence of interaction between the electronic and nuclear states. Specifically, in our experiment, we dissolved lithium bromide salt into a thorium nitrate solution, and we also prepared a control solution, and we compared the nuclear radiation signatures of these two solutions. We repeated the same experiments to analyze separately the X-ray spectrum and the gamma ray spectrum. The X-ray spectrum was measured between 1 and 20 kiloelectron volts, and the gamma spectrum between 20 and 3000 kiloelectron volts. So in this slide you can see the peaks which we have analyzed, and we find this very surprising reaction signature that after our experiment it takes some hours for the activation to happen, and during these hours up to 6-7 hours after the experiment we can see a continuous rise in both the X-ray and the gamma signatures, and thereafter the intensity of the peaks gradually goes down to the normal levels before the experiment. So in this way the X-ray and the gamma spectra, their tandem evolution gives complementary views of the undergoing reactions. And what we find when we look closer into these gamma signatures is that the isotopes which are activated are actually PB212 and its downstream isotopes, which means that we are observing a cluster fission that takes us from thorium down to a smaller, lighter isotope. And what we can see in the X-ray spectrum is that we have a very sharp rise, especially in the L-alpha 1 line of thorium. This is this very narrow peak that you see in the chart, and then downstream with the bismuth and TL isotopes. So this is a interesting case of a nuclear activation that must be caused by a special electron state, because it's not a fully activated state after our experiment, but it gradually activates after our experiment, which proves that we have created a special electron state that gradually activates or catalyzes the nuclear fission in thorium. And this electron state we also have been analyzing by the XRF method. Specifically in the lithium bromide salt that we dissolved, we identified a component that we could extract, so-called sediment, and when we look at the XRF signals of the sediment, specifically in the bromine response, we see an anomalous difference with respect to any other bromine compound that we have analyzed. So this is a very interesting diagnostic that we have with the help of XRF to identify anomalous rearrangements in the inner shell. And what we see in our experiment is that we start with bromine, some bromine contaminations, let's call it this way, that contain a special inner shell electron state, and this inner shell state is then transferred to the thorium, and this inner shell rearrangement of thorium's electrons is what appears to catalyze its nuclear cluster fission.
In order to understand the chemical environment, we performed an atomistic simulation for half a picosecond of dissolution in the hydrated thorium nitrate. We did this using ACE and the orbital materials ORB-V3 inference, which was already validated for lithium bromide atomic potentials. We can see that the three-body coordination is dominated by lithium oxygen bromine and thorium oxygen lithium bonds. And this gives us a good starting point to try and understand how nuclear vibrational tunneling can occur between thorium atoms, and also which atoms contribute to the energy surface. In particular, we know that these two thorium atoms are bridged by two oxygen atoms in this hydrated thorium nitrate. Since both electronic and nuclear wave functions are both represented by spherical vector harmonics, it makes sense for us to understand them at a very fundamental level. In the multipole expansion, it's academic convention to truncate the spherical vector harmonics to the second order so as to avoid including these ugly nonlinear terms. And obviously that's a successful approach because it produces all quantum chemistry, the whole periodic table, and you can say the same for the nuclear context. Its predictive power is extreme. In contrast, though, if we include those ugly nonlinear terms, when we don't truncate the spherical vector harmonics, we can describe wave packets on an energy surface that has increased dimension up to the codimension of the phase space. I devoted my previous talk on the thermodynamic limits of such an energy surface at the vacuum level. The most exciting aspect is understanding the fast ion motion introduces these high order terms that are usually neglected, and it does this through local polarization. And if you think about in any, like a superionic conductor is one where you have a lattice, and inside a lattice the ion motion is large and high. So for an anti-perovskite, you'll have an A3, and the A3 ion will move inside the BX cage. Typically, you'll see a Coulomb barrier represented on a one-dimensional energy surface. But the reality is that tunneling occurs on a much more rich manifold, and that's especially true for superfluids and superconductors. Here's the radial, electric, and magnetic vector fields, and you can see the expansion for the vector potential using the harmonic terms. In this case, it's non-truncated because we include this toroidal vector harmonic term down here, and you can see it applies to the radial component. For a dissolution or any other van der Waals mediated energy surface, the quadrupole-quadrupole interaction contains this toroidal component, which is otherwise completely dropped. This, just by itself, can introduce the anharmonic resonant energy transfer mechanism. And this is the theoretical path that we'd like to pursue. In conclusion, we observed altered electron states in the inner shell region, and these electron states catalyze nuclear cluster fission. We'd like to selectively excite these electron states to modulate decay rates. I would like to thank Andras, who really led this investigation, Heikki Sipilä for access to the amazing detectors, and Dennis Pease for his advice throughout. There is a preprint. It's not really ready for dissemination, but feel free to reach out to either Andras or myself.